what you're going to notice is this neutrophil is chasing a streptococcus bacterium. He wants to eat it. And it goes left, it goes right, it changes direction, it speeds up, it slows down. It makes all of these decisions based upon the way information exchanges from molecules talking to one another. We always think of molecules as being as A binding to B or B binding to C. But the reality is, when they bind to one another, they're transferring information. We're conditioned to think of information as zeros and ones. But what you saw there was a clear example that information occurs in these molecular interactions. When I talk tomorrow, I think it's tomorrow on the biological computer, we'll talk about trying to harvest some of these elements. But in the meanwhile, what you want to know is understand is if you have all these pieces talking together, what are these pieces and how do they fit together? What you'll see is that during the agriculture and mechanical age, everything in our society was built from the 6 simple physics machines. So everything from a Babbage computer to your plow was all built from these same simple machines. Today, in our modern age, everything is built from 5 additional fundamental components. So we have 11 fundamental machines that we use to design our technology in our entire society. Everything that we build, we've broken down to those machines. Now, contrast that with living systems. Living systems have many, many hundreds of thousands of different machines. We call them proteins, we call them enzymes, we call them nucleic acids. But what they do is they provide unit operation of function. They transduce power, they pump, they select, they sort, they do all these functions. So when you look at the molecule in abstract, you say, oh, A binds to this. If you step back about a meter and you start looking at what it really does, not of the eyes of a biochemist, but of the eyes of an inventor, you say, oh, these things are a component piece, and we can go and make things. Just like you could make a crankshaft with the elemental components to create a reciprocating engine, the 6 simple physics machines, we could do the same thing. Now the challenge is, how do we take those machines and put them into an environment that's engineering relevant? What you find is that to make this happen, several things have to occur. We're going to talk about several of those features right now. One of the most principal things is you need to get energy into the system at the same size scale. You have to get the energy to allow those molecules, those machines to run, do what you want to do. Second thing you need to do is you need to get local compartmentalization. Because what happens is, if you're going to start building these simple machines and putting them in systems, you can't start thinking of molar concentrations of machines. You start thinking of individual molecules. And to make the chemical reactions, to make the interactions occur, you need to be able to have them close together so the reactions happen. So you have to compartmentalization. Next thing you have to do is you have to do precision assembly. You have to do nanotechnology. You have to get them oriented and placed the way you want to. So they're placed in the right direction to do what you need to get done. So you need to be able to have them to be stable. So you need to have them in an environment where they're stable in an engineering relevant environment. You need to solve all these problems. And for the last 15 years, I've been working on trying to solve these problems. And you know, one of the first things that we did was we needed to make a stable system for assembly. So we developed a block copolymer structure that has the same principal structure that you would find in a membrane in a living system, except if you cross-link it, it has the physical properties of plexiglass, and it withstands pressures of 10,000 psi, and it allows these molecules to keep on functioning well beyond 60 degrees Celsius. So all of a sudden we make these, we figured out how to assemble them into component pieces, into vesicles that you want, and then we start from that basic component. We started assembling our first system. We call them artificial organelles. So the first thing was an energy transduction system. In this system, we did our first step for energy transduction to produce ATP. ATP is the energy of life. And every day, 1/2 of your body mass undergoes a transformation of going from ADP and phosphate into ATP, and then back to ATP and phosphate. one half of your mass every day. It has an operating efficiency of greater than 99%, and it operates at warm temperatures. Very new, by the way, is we submitted it to Nature to be published about a week ago. Right? When we couple photosystem 2, and photosystem 2 comes from E. coli bacteria, it's this big giant monster of a molecule. And then we have complex 1. We put the two together, which you just add some light, which you end up with is a new type of artificial organelle that never existed before. One that can go and produce NADH from just using light, using a process which is very, very similar. And what you find is that when you build this system, which we built, is that you cycle it and it works, it keeps on working, it works fine. So we developed a system now that allows us to take NADH, and we're able to do it with a
information technology.
But I won't talk about, when I talk about the ionic computer, I'll talk about stochastic information exchange. That's ionic currents that we're looking at, that models the way the brain processes information. Because, we process information, since the 1940s, we've all decided that all information is zeros and ones. Living systems, the information is not zeros and ones. It's a construct that was developed because what we had was those 11 building blocks that we could deal with.
Thank you.
Look. When I use, first off, both of those systems I showed you, they don't exist in nature. I took pieces that I found in nature, and so because I took pieces out of nature, I'm able to sidestep it. The photosynthetic process is actually a lot more complicated than the system that we're building, and by taking pieces out of different species, they don't share the same genetic materials. We're able to engineer a system that has the function that we want.
Okay, the particular gene, we need to engineer.
Well, we engineer the gene, we express the gene, purify the protein, then we take that purified protein and put it into our system. So there's nothing alive. There's absolutely nothing alive. You're welcome.
Very adept in biology, but when reading about photosynthesis, one understands that we have forgotten the name of the particular piece of the cell which actually produces.
We take these fundamental building blocks and we put them together through our own ingenuity. We're going to be able to do things that nature never intended them to do. And because they've been designed to operate at extraordinarily high efficiencies, you end up with making extraordinarily efficient machine systems.